Okay, so welcome to another tutorial session, and today we are going to talk about stationary waves. Okay, so there are progressive waves and then there are stationary waves. So progressive waves are traveling waves, whereas stationary waves are waves that are trapped, so they are stagnant. And a wave, when trapped, indicating that it's stationary, can be trapped in something known as air column, aka pipes. Okay, so anytime you hear the word air column or pipe, we are basically referring to the same thing. Now, this is the premise for wind instruments. Okay, so with wind instruments, we are looking at the flute, the trumpet, the trombones, etc. The base of this is about the frequency. The frequency is the fundamental frequency. So we need to establish the fundamental frequency in any of the pipes. So in this case, we are going to start with the closed pipe, as you can see the diagram on the screen. Okay. So we are going to establish the fundamental frequency of a closed pipe. Then we look at the harmonics. The harmonics is also known as the overtone. So when you have more or a lengthy stationary wave trapped in a pipe, the sound is going to change. So that is the overtone. All right. So how do we ascertain this? So we start by looking at a regular air column. All right. So you can see the air column with the wave trapped inside of it. So this is the wave that is trapped inside of the air column here. So the open end is what is known as the antinode. Okay. And then the closed end is known as the node. Now, this is the length of the pipe and is denoted by the letter L. And then this is the length of the wave. Okay, so this is the wave. This is the wave trapped here in the pipe. Okay, and it is 1 over 4 lambda. The assumption is that the wavelength, which is 1 over 4 lambda, is equal to the length of the pipe. So that is the assumption. So we can instantly say that this is lambda over 4 and consequentially say that lambda is equal to 4L from our mathematics when we do the change of subjects. Right? But then you remember this formula, the formula that links velocity of a traveling wave to the frequency and then the wavelength. So since we are saying that, so we are looking at the fundamental frequency in a closed pipe. Since we are saying that lambda is equal to 4L, which is 4 times the length of the pipe, then anywhere we see lambda, we put 4L there. So we can see that V, and I've emphasized that the frequency here is the fundamental frequency, right? It's 4 times the length of the pipe. So this is the expression that we have at the moment. But because we are looking for the fundamental frequency, we make the fundamental frequency the subject. So we go ahead to divide here by 4L, divide here by 4L. These cancels out. And F naught equals V over 4L. So beyond the fundamental frequency, if we want to find the first overtone, Okay, so when you have more air trapped inside the column to form the first overtone, this is what happens. So this is how the diagram looks like. So we have the our node down here, we have another node down here, and then there's an antinode on top. So always remember the open end is an antinode. So this side is 1 over 4 lambda, just like you can see from here. Okay. So this side is also 1 over 4 lambda, or 1 over 4, 1 over 4. When we put all together for the wavelength, it becomes 3 over 4 lambda. All right. And we've established that the length of the pipe is equal to the wavelength. Okay. So we can multiply 2 by 4. So it becomes 4 times L equals 3 over 4 lambda times 4. This cancels this, so we have 4L equals 3 lambda. We want to make lambda the subject of this equation. So when making lambda the subject, we divide through by 3, and then we cancel out. So all we have now is 4L over 3 equals lambda. But you remember this equation, V equals F lambda. Now, because we are working with 3/4 of the wavelength, and we want to differentiate the fact that the frequency here is different from the fundamental frequency. So this is the first overtone. So we write here F1. Okay. So our V F1 therefore becomes, anywhere we see lambda, we put 4 over 4L over 3 there. So putting this equation in its right format, we can multiply 2 by 3. So this side by 3, this side by 3. This goes away. So we have 3V equals F1 multiplying 4L. But we are looking for the first overtone, which is F1. Okay. So we can divide 2 by 4L so that our F1 stands alone. We end up having F1 being equal to 3V over 4L. But notice this, our fundamental frequency here is V over 4L, this side, V over 4L is our F naught, which is our fundamental frequency. So we can say that our first overtone, which is F1, is equal to 3 times our fundamental frequency. What's the implication of this? It means that closed pipe will only give you odd harmonics. So if you have your first frequency, which is your fundamental frequency, you have your first overtone, it's you have your second overtone, You have your third overtone. Sorry, let me rewrite this. My bad. You have your third overtone, which is F3 in that order. Because we know that the first overtone is 3 F naught, we can use the same procedure to generate the other overtones with respect to our fundamental frequency. Mind you, I said earlier on that closed pipe only produces odd harmonics. So from 3 F naught, we go to 5 F naught, 7 F naught in that order. Okay. So this is the trick. A question can be given. Then you are asked to find the second overtone. Because you know this F naught is the fundamental frequency, this is the first overtone, this is the second overtone. The fundamental frequency will be given, then you just multiply it by 5. Then you have the answer for your second overtone. Okay, so this is all there is to closed pipes. Now let's look at open pipes. So for open pipes, okay, we are starting off with the deduction of the fundamental frequency. So how do we find it? So for open pipes, because both ends are open, we have antinodes at the extreme ends. Then we have our node in the middle. We've already established from closed pipes that this is 1 over 4. This is 1 over 4. So when you put the two lengths together, you have 1 over 2 lambda, which is the wavelength. All right. And we already know that we are working with the assumption that the length of the pipe is equal to the wavelength. In this case, 1 over 2 times the wavelength, or half a wavelength. Our equation can therefore be manipulated because we want to know the value of lambda. We multiply both sides by 2. This goes away. So you have 2L equals lambda. All right. But our velocity and then the frequency we are discussing here, which is our fundamental frequency, times lambda. So our V equals F lambda. This is what we know. And then we know that lambda is twice the length of the pipe. So anywhere we see lambda, we put 2L there. Okay. Since our main focus here is to find the fundamental frequency, so we make F naught, which is the fundamental frequency, the subject of the equation. So let me put that down quickly. So we are going to divide all the sides of the equation by 2L. So 2L here, 2L there. The 2L over 2L to our right cancels out. And then our fundamental frequency becomes F naught equals V over 2L. So this is how you find the fundamental frequency in open pipes. So for our first overtone in open pipe, we know this side is 1 over 4, This side is 1 over 2. This side is 1 over 4. So putting all together will give us 1. So our theory now is the length of the pipe is equal to lambda, right? So we go again with this equation. Because we are going to use this wavelength here to show that this f is different from this f, okay, we call this f1 because the wavelength has changed, which is our first overtone. So anywhere we see lambda, we put what? The L there. So V equals F1 L. Now we want our L to stand alone. Okay. We want our F1 to stand alone, not our L. So we divide here by L. We divide here by L, which is our length. So our F1 becomes equal to V over L. But we are not done. You see, anytime we get the value of our first overtone, we try to link it to our fundamental frequency, okay, which is F naught. Look at this. Look at this equation. This equation can be expanded to F naught equals V over L here. Let me put the 2 aside. Yeah, so 2 dot L. The 2 is multiplying the L. Alright. So we can have it in this way. If we multiply 2 by 2, so we multiply this side by 2, multiply this side by 2. These are 2 cancels out. We have 2 F naught equals V over L. So this is the same as this. Alright, so anywhere we see V over L, we put what there? 2 F naught there. So in this situation, we are going to say our F1, which is our first overtone in the open pipe, is equal to 2 times the fundamental frequency. And we are done. Right, so it's not too difficult to comprehend. So it means that in an open pipe, when we have our first frequency, which is our fundamental frequency, it is followed by our first overtone, which is twice the fundamental frequency, right? Then 3 F naught in that order. So in open pipe, we get both even and then odd overtones, or even and odd harmonics. All right. Now, how do we employ all this? Okay, these are all hypothetical scenarios. But then before we move on to look at its application, we would also have to look at another concept known as end correction. So this is a diagram trying to depict end correction. I've not brought in the end correction bit yet. But you see, the ideal situation that we propose is that the length of the pipe is equal to the wavelength. Okay. But then in reality, it is not so. You have the wave extending in length. Okay. It extends in length. That is the practical thing, or that's the reality. So we have to account for that. Okay. Because we want everything to be accurate. So it is noted as, or denoted as C, which is end correction. So in that way, if we are looking for the fundamental frequency, the equation is going to change a bit, not too much. In what way? All right, so this is it. So before, we knew that the length of the pipe is equal to the wavelength in this case, which is 1 over 4 lambda. But you see, because we have added n correction, we have to account for it. So plus c. We can put it in a bracket nicely here. Okay. So in calculating for lambda, we can multiply the side by 4, multiply the side by 4. This goes away. So lambda is therefore equal to 4, open bracket, L plus C. Okay. So when we want to substitute this into this equation, it is going to look as such. Our V equals F naught, where our lambda is now 4, open bracket, L plus C. So if we are making F naught the subject, it therefore becomes F naught equals V over 4 L plus C. So you see, it hasn't changed much. Where you find 4L, there is a C there to multiply it. Okay. What's the end goal? The end goal is that we use this equation to solve more practical questions that we are confronted with regards to closed pipes or open pipes, right? So let's take an example to reassure ourselves in the grounding of the theory that we just experienced. So this is our example, and I read, in a resonance tube experiment, the first position of resonance is found to be 20 centimeters, and the end correction of the tube is 2 centimeters. If the velocity of sound is 330 meters per second, calculate the frequency of the tuning fork. So I have tried to mimic the experiment here. So this is our resonance tube with water in it, and this is the first position of resonance, which gives us our wavelength. And you know this wavelength is 1 over 4. So our first position of resonance is our fundamental frequency. Okay. So this is practical in nature. When the question says that you should, when the question adds n correction, okay, you take into account n correction. When n correction is not given, then it means that you can neglect it. Okay. But these are the values given: the length of the resonance tube, which is 20 centimeters, and we change that to meters, giving us 0.2 meters. Then we have n correction, which is C, as 2.0 centimeters. We convert that to meters, which is 0.02 meters. Now our velocity is 330 meters per second. And then because we are taking into account n correction, our fundamental frequency equation is going to look something like this. F equals V over 4, you open the bracket, L plus C, then you close the bracket. So we just fix in our values and we are good to go. So V here is 330 all over 4. You open the bracket, 0.2 plus 0.02. I think we end up with 330 over 0.88, which gives us 375 hertz. So as simple as that. This is how you deal with questions involving vibrations in pipes.